Introduction to power systems. In introducing the second law of thermodynamics in Chapter 7, we considered cyclic heat engines consisting of 4 separate processes. We noted that this engine can be operated as a steady-state device involving shaft work, or a cylinder piston device involving boundary movement work. The former may have a working fluid that changes phase during the process in the cycle, or may have a single phase working fluid throughout. The latter type would normally have a gaseous working fluid throughout. For a reversible steady-state process involving negligible kinetic and potential energy change, the shaft work per unit mass for a reversible process involving negligible kinetic and potential energy change the shaft work per unit mass or a specific shaft work is equal VdP. For a reversible process involving a simple compressor substance, which is for shaft work, for a simple compressor reversible process, compressible substance, the boundary movement work per unit mass a specific boundary movement work. PdV. The areas represented in the next picture. The areas represented by these two integrals are shown in this picture. It is of interest to note that in the former case, there is no work involved in the constant pressure process, while in the latter case, there is no work involved in constant volume process. This is a shaft work, VDP, and this is the boundary movement work, PDP. Let us now consider a power system consisting of a four-stage process as a figure shown in this picture. For a steady state process shown in this picture, we assume that each process is internally reversible. And has negligible change kinetic energy and potential energy change approximately zero, which results in the work for each process being given by the equation W equals VdP. Thus, the for convenience of operation, we will make the two heat transfer process, boiler and condenser, in this boiler and condenser, constant pressure process, boiler and constant pressure, such that those are simple heat exchanger involving no work. Let us also assume that the turbine and pump process are both adiabatic process and are therefore isentropic process. Delta S0. Reversible adiabatic means isentropic. Thus, the four processes comprising the cycle are shown in the next picture. Note that if delta, we have two constant pressure, boiler, pump, and turbine. Note that if the entire cycle takes place inside a two-phase liquid vapor dome in the resulting cycle is the Carnot cycle, since two constant pressure processes are also isothermal. Otherwise, this cycle is not a Carnot cycle. For the Carnot, for non-isothermal process, we don't have Carnot cycle. In either case, we find that network output for this power system is given by this relation. Network output for this power system plus 0. We start with this point. The first is a pump work, 0 work, turbine work, and again on the same 0 work. These quantities can change. And since P3 and P1 equals to P4, we have this we find that the system produces a network output because the specific we find that we have a W net because we have different function for V in each integrals. V equals to a function, for example, of P during this diagram. This is also evident from the areas in this picture network. We conclude that it would be advantageous to have these differences in a specific value be as large as possible, for example, the difference between a vapor and liquid. So, higher specific volume difference to higher work. If the 4-process cycle shown in this picture were accomplished in a cylinder piston system involving boundary movement work, then the network output this power system can be changed and is so if we have 4 cycles in accomplishing in a cylinder piston system, we can have this relation. And from those 4 areas in the picture below, we note that pressure is higher during any given change in volume in the 2 expansion process than in the 2 compression process, resulting in net positive area and a net work output. Excuse me. PV diagram can be. We don't have a constant pressure processes. For either of 2 cases, just analyze it is noted from the figure that the network output of the cycle is equal to the area enclosed by the lines 1, 2, 3, 4A, and this area is the same for both cases, even though the work terms for the 4 individual processes are different for the 2 cases. In this chapter, we will consider the first of the 2 cases examined above, a steady-state flow process involving shaft work, utilizing considering working flows such as that difference in the network relation between the expansion and compression process is a maximum. We will consider the first of 2 cases, a steady-state flow process involving shaft work, utilizing condensing working fluid, such that the difference in the network terms between expansion and compression process. In Chapter 12, we will consider systems utilizing gaseous working fluid for both cases, estimate a steady-state flow system with the shaft work terms, and piston cylinder system involving boundary movement work terms. In the next several sections, we consider the Rankine cycle, which is the ideal for a steady-state process cycle, utilizing a phase change between vapor and a liquid to maximize the difference in a specific volume during expansion and compression. This is the idealized model for a steam power plant system. The next section is the Rankine cycle.